The question here is, could you do an example on the calculation of the shear stress in symmetric bending? And in this particular example, I'll take the cross-section to be a symmetric I-beam. So here's the definition of my problem. We have a horizontal beam subjected to a shear force of 20 kilonewton on this vertical plane. Here is the cross-section of the beam. We want to calculate the shear stress due to the shear force at these points A, B, and C. So with respect to this line that divides the flange from the web, point A is taken just in the flange, point B is taken just inside the web. Point C is right in the middle, which is the centroid of the cross-section. And here are the three relevant axes. X-axis is the neutral axis, that is the axis that passes through the centroid of the cross-section. And Y is the vertical axis here, and the Z is the axis perpendicular to the paper here. And both of these axes are also placed at the centroid of the cross-section. Here is the general formula that could be used for any cross-section for calculating the shear stress due to a shear force. So how do we use this equation? Well, we'll take the point where we want to calculate the shear stress at, and then draw a line parallel to the z-axis, divide the cross-section into two parts. For example, if I'm interested in calculating the shear stress at point A, I will draw a line right there, right, and divide the cross-section into two parts. The shaded area is one part, and this unshaded area is the other part. And you can use either one of these parts in your calculations, but here, conveniently, we will use this part right there. Q appearing in this equation is the integral of y times dA over this shaded part. Let's say the cross-sectional area is A prime. So Q is obtained by integrating this quantity over A prime. I appearing in this equation is the second moment of inertia of the entire cross-section about the z-axis. So this is independent of the point that you are considering. This is the sectional property. Now T here is the width of the cross-section perpendicular to the paper at the point of interest. So if I'm interested in point A, that will be the width, right? But of course, the width is going to depend on whether you are taking the point inside the flange or inside the web. If I take the point to be inside the web, such as point A, then the width will be the width of the entire flange, which will be 200 millimeter. On the other hand, if I take the point to be just inside the web, like point B, then the width is going to be the width of the web, which is 75 millimeters. So suddenly it decreases drastically, right? Similarly for point C, we'll draw a line right there, right? And then divide the cross-section into two parts. Obviously, this time we are dividing the cross-section evenly in half. So you can consider the top part or the bottom part. Here we will consider the top part. Then Q is the integral of the shaded part, which is half the cross-section of the I-beam. And the T will be the width of the web. So here are the details of the calculations of the values of Q for the 3 points, points A, B, and C. For both points A and B, we have the same shaded area, and therefore Q's are going to be the same. This integral is also equal to A prime multiplied by y bar prime, where A prime is the area, y bar prime is the distance, the centroid of the shaded part, measured from the center of the beam C, right, which is 175 millimeter. All right, so A prime is 200 millimeters. So let's use meter as our unit of choice for linear dimensions. So that'll be 0.2 meters, right, multiplied by the thickness of the flange, which is 50 millimeter, which is 0.05 meters, and multiply that by y bar prime, which is 0.175 meters. So that is calculated to 1.75 times 10 to the minus 3 meter cubed. So for point C, we have to use the idea of the composite section to deal with this shaded part, because this has two rectangles in there, right? So we'll divide this along this line into two sub-rectangular sections. This part right there, the flange, and half of the web. QC then is A1 prime multiplied by Y1 bar prime plus A2 prime multiplied by Y2 bar prime. So here are the details of the calculation, fairly easy to follow, so I'll let you follow through. And here are the values of T for the 3 points. Like we said before, point A is taken in the flange, and therefore the value of T for point A would be the width of the flange, which is 0.2 meters, whereas point B is taken in the web. The width there is 0.075 meters, and point C, of course, is right in the middle of the web. The width there is 0.075 meters. Now let's go ahead and find a value for the second moment of inertia. Since we have an I-beam, we're going to have to break it into sub-rectangles. And so in this case, I'm going to break it like shown in this picture here. This is my area number 1. This is my area number 2, basically the area of the web. And then the bottom flange is area number 3. But we recognize that area number 1 and area number 3 are identical, and therefore all I have to do is multiply the second moment of inertia of A1 by 2 in order to account for this bottom flange. Now remember the formula for rectangles, right? 1 over 12 BD cubed. But that formula only will give you the second moment of inertia about an axis that passes through the centroid of the rectangle. But if the centroidal axis does not coincide with the z-axis, then we're going to have to use the parallel axis theorem in order to account for the eccentricity of that section, right? So here's the equation associated with the parallel axis theorem applied to a composite section. So here IIC is the second moment of inertia about the centroidal axis for segment I or section I. Then you add this term in order to account for the eccentricity of the centroidal axis from the z-axis. So here we have the AI, which is the area of the section, multiplied by yi bar squared. Yi bar is the distance, the centroid of that section from the centroid of the overall, the entire section, right? In other words, that's the distance between the global z-axis and the local z-axis, right? So that distance right there. So expanding this in a specific manner for what we have here, we have 2 times I1c, which is the second moment of inertia of the flange about this axis, the local axis, plus A1 times Y1 bar squared, where A1 is the area of the flange multiplied by Y1 bar, which is the distance to the centroid, which is this point right there from this point. And here we have 175 millimeter for that, right? So square that, plus it turns out that the centroidal axis for the web coincides with the z-axis. So we don't have this area term for that section right there. So that'll be just I2C. So here are the numbers to go with that equation. So let's kind of go through this quickly. So 2 multiplied by 1 over 12 times B, which is the width of the flange, which is 200 millimeter or 0.2 meters, multiplied by the depth of the flange perpendicular to the z-axis here. So that will be 0.05 meter cubed plus area of this section is 0.2 multiplied by 0.05, and the distance to the centroid is 175 millimeter or 0.175 meter, and we have that over here. So you square that, plus the second moment of inertia of the web would be 1 over 12 times B, which is this part right there. So that will be 0.075 meters multiplied by this distance, which is the depth, which is 0.3 meters cubed, right? So you simplify that, we get this value for the second moment of inertia of the I section about this global axis Z. Now that we have all of the key parameters appearing in this general equation evaluated, we can go ahead and calculate the shear stress. So here is a list of the values we've calculated in the previous slide for these parameters. And here are the details for the numerical calculations. Let's go over one of them and you can follow the rest fairly easily. So let's say we want to calculate tau xy at point A, right? So it'll be VQ over IT evaluated at point A. V, of course, is the same for all the points. V is 20 kilonewton. Q differs from point to point, but at point A, it's 1.75 multiplied by 10 to the minus 3 meter cubed. I is constant for the whole cross section, so it doesn't vary from point to point. It's the same value. The value is 0.786 multiplied by 10 to the minus 3 meter to the power of 4. And T, of course, varies from point to point. And for point A, it's 0.2 meters, right? 0.2 meters. So you simplify that. You can see I can cancel this 10 to the minus 3 from the numerator and the denominator. And just writing the remaining numbers, we have a simple equation. The equation is 20 multiplied by 1.75 over 0.786 multiplied by 0.2. And the unit is going to be kilopascal. We have kilonewton here, and we have meter to the power of 5 in the denominator, meter to the power of 3 in the numerator. So this is going to be kilonewton per meter squared or kilopascal, right? So this simplifies to 222.6 kilopascal. In other words, the shear stress at point A is 222.6 kilopascal. And this picture right here shows the directions of the shear stresses drawn on a two-dimensional differential element at these points. Now you repeat these calculations for point B and C, we get these numbers. So the value at point B is 593.7 kilopascal, and the value at point C is 882.1 kilopascal. So you might remember this picture for an I-beam, right, from your basic theoretical analysis section, right? So this value right here is 222.6 kilopascal, and suddenly it jumps to a value of 593.7 kilopascal as soon as the point falls in the web. The maximum occurs in the middle, and the value is 882.1 kilopascal.